integrated direct communication mobile networks by limited software, sending email to, and it just explains everything.
Hello, so I'm Pitoura from the Department of Informatics and Communication from the National Catholic University of Athens, and I'm going to discuss today about integrating direct communications in mobile networks. Okay, so our mobile phone today can do anything. It's a very powerful device, potentially to make coffee if you connect your mobile application to your coffee machine. However, what it cannot do is do what the traditional walkie-talkies did. They cannot talk to each other. So device-to-device communications have actually come to solve this problem. In device-to-device communications, two mobile users which are in proximity to each other are able to communicate directly by passing the base station. Perhaps you can understand that this brings a lot of benefits both for the end user and the mobile network operator. For example, we have decreased latency, we have less power transmission due to the close proximity between the two devices. We have as well, we can achieve offloading of the whole mobile network, etc. Moreover, it can enable some critical communications, for example, in cases where the base station is down, or through device-to-device relays, extending in this way the coverage of the cellular network. Moreover, it can enable machine-type communications and IoT services. 3GPP has shown great interest in direct communications. It has standardized them to some extent, starting from what is called process proximity services, and this can be used even for vehicle-to-vehicle and vehicle infrastructure communication. So some dominant research challenges that we need to overcome before device-to-device becomes a reality. The first one has to do with device discovery, so devices have to identify each other and meet each other in space, time, and frequency. Then there's a problem of mode selection, which means that we need a mechanism in order to switch efficiently from the cellular to the direct communication mode and vice versa. And this has to take place in a very challenging dynamic mobile environment. And the last challenge that we have identified has to do with the user experience. So we have to make sure that this new communication mode brings benefits for the user experience, and that perhaps this can also be used in order to drive the management process. Some results from our research that map to these previous research challenges. Regarding the device discovery, we have proposed an algorithm which takes into account the social history, and in this way we can decrease the amount of the required transmissions in order to discover our neighboring devices, which has shown to perform much better from a random access model or even a central allocator. Then some results about mode selection. We have implemented an algorithm in the simulator Omnet++, where we have successfully managed to switch the communication from cellular to device mode and vice versa, based on what is called the network channel quality indicator. And finally, we have proposed a charging model where the users are charged based on the quality of experience that they actually get due to their device-to-device communication mode, as compared to the one that they would get if they would be connected in the cellular network. I think I'm exactly 3 minutes. Thank you very much.
So let's go again for being on time. And the next work is by Alexandra Sigani and Christos Tsiotis. And Alexandra is presenting.
such as beam splitters, phase shifters, single photon sources, and photodetectors. Some examples are shown here. The scope of our work is to use integrated optical circuits for enable linear optical quantum computers, especially in silicon-silicon platform, which is a widely used platform in telecommunications, sensing, and also compatible with fiber optics. The integrated optical circuits will be implemented by femtosecond laser writing techniques because it enables 3D adiabatic waveguide description by adjusting the focus of the laser beam, and also we can induce accurate micro-machined regions, and a schematic is shown here of our communication system. A specific step in our study is the integration of the quantum emitter in an optical waveguide, which is a critical step for enabling scalability in quantum circuits. In order to create such quantum emitters, we need to accurately place the nanowire quantum dot by special tools in a tapered waveguide through a micro-machined slot, as we see in the slide. Also, for optimization, we inscribe bright ratings in order to increase the directionability of the quantum emitter. By placing multicolor qubits, will enable a scalable quantum circuit. In order to handle the signal and the multiple quantum emitters, we are using wavelength division, multiplexing components, and other tools previously developed in telecommunications industry. This way, we can have photo processing components on chips, and some emerging applications are in security, machine learning, biomedical modeling, and etc. Thank you.
Work is by Sofia Menachiotti and Vasilis Mamalis, and Sofia is presenting. Yes.
Hello, my name is Sofia Menachiotti, and I'm going to present you a clustering algorithm for big text data using MapReduce. Document management has become, over big text data has become of high importance now more than ever. Clustering is an efficient machine learning method, while K-means is the most commonly used clustering algorithm, presenting high quality results and low cost. However, it can lead to unpredictable time costs when applied to big text data, since the duration of iteration tends to grow as the number of iterations grow. Towards the direction of an effective solution for big text data clustering, we adapted a K-means-based algorithm known as big K clustering, primarily developed and tested for big point data, so that it can be applied to documents represented as weighted n vectors using MapReduce. We represented each document as a key value pair, where the key is the name of the file and the value is a vector with multiple components, the main being the TF-IDF weight of each term in the document. Cosine similarity is used as the comparison measure due to its efficiency when we are dealing with high-dimensional data, such as text documents in the vector space. The two core components are microclusters, who are in fact clusters of restricted size represented by a suitable vector, and the equivalence relation that provides us with formula in order to decide whether two microclusters are similar enough and should be grouped together. This is an overview of the basic steps of the approach. We first choose a number of initial centers from the original dataset, and each document is assigned to the most similar center. This is a step that equals to one iteration of K-mix. We then construct the microcluster vectors from the clusters created in the first step. We initialize a variable called connection similarity as the mean value of the minimum cosine similarity values in each microcluster. and then apply the equivalence relation to form groups and to merge microclusters. We adjust the value of the connection similarity if needed and reapply the equivalence relation until the number of groups is equal or adequately close to the desired number of actual clusters. When the groups are formed, we calculate the centers for the groups and apply a final round of k-means. We implement the algorithm using Apache Hadoop and Java. The datasets used were the 20 musical collection as well as synthetic collection of almost 1 gigabyte. The results were quite promising since we observed significant time improvements, up to 50% compared to the duration of 4 iterations of k-means, and up to 95% compared to the total time required for convergence of k-means. At the same time, quality of clustering was kept in acceptable levels. Thank you.
The next work is by Pitoura, Νικόλος Καριβάνης, Ελένη Κανέλιου, Οδυσσέας Μακρυδάκης και Κρίστης Λεωνίδου. Και παρουσιάζει η Ελένη, σωστά? And Eleni is presenting.
So, hi all, I'm Eleni, a postdoc at ICS 4th, and I would like to start this talk by inviting you to check how many cores you have on your portable devices. Which is a rhetorical question, of course, because I'm sure that you have at least 4 cores or more. And the trend is that this number will grow in the future. And moreover, the larger the computing scale, the larger the predicted number is going to be. This is why we say that we're now firmly in the multi-core era, and we're even moving towards the many-core era. From the software point of view, this means that we're also in the concurrency era, and up to now, multiple cores on a single chip have meant that concurrency relies on the shared memory abstraction. The shared memory abstraction, in turn, relies on hardware cache coherency. However, on the many-core level, cache coherency is no longer sustainable, so now the industry is moving away from that and is moving towards partially or even non-cache coherent architectures. In the foreseeable future, you have architectures like the ones that I'm illustrating in the slide, where the memory is divided over multiple modules, and cores share them possibly in coherent silence and communicate between them through the message passing paradigms. This, of course, poses a problem for software productivity. I will take Java as an example. Java is a language that is highly portable and highly productive because it offers many libraries with ready-made objects that can be used by programmers to complete their projects. In terms of concurrency, Java has the concurrency utilities package, which contains implementations of shared data structures. And those data structures can be used even by a naive programmer that has no idea of concurrency or a small idea of concurrency to be very productive in software development. However, these libraries rely on the shared memory abstraction again, which is a problem in the non-cache coherent era. And I hope that this makes the case for why data structures are crucial for portability in the many-core era. So we have to design them with new architectures in mind. So this is exactly what we wanted to do. Our work is the first step towards designing customizable data structures that will be scalable with the number of cores that are added to the new architectures. To do that, we had to study several techniques for implementing data structures and face challenges such as the fact that shared memory is no longer there. You have non-cache coherent or at least partially cache coherent architectures, and you have to use the message passing paradigm efficiently. We chose several techniques. We combined them to come up with variations of data structures, several implementations, for example, of stacks, of queues, of double-ended queues, lists, sets, etc., each designed with several different techniques in order to have variety and be able to attest their efficiency on the new style of architectures. And our goal was to provide a collection that can be utilized in high productivity languages for easier porting to new architectures and as a library for non-experts. We also performed experiments on the designs we created on a custom in-house prototype of 512 microblaze cores. And we found some nice properties and some interesting results. For example, we found that optimizations evidently play a big role in scalability, so customizing the data structure to the architecture makes the data structure more scalable. We found that techniques that offer a fully distributed storage, let's say, of the data structure over all the modules of memory, plus some hierarchical communication scheme, gives good scaling properties. On the contrary, more server-oriented storage techniques are maybe suitable for smaller data structures, but do not scale very, very well. And we found that the total number of messages doesn't seem to play a big role. So I would like to show you the blue line in this case that shows nice scaling properties of data structure. The number of cores on the x-axis increases. And with this beautiful result, I would like to lure you to join me for the poster outside for more details on the techniques. Thank you very much.
By Eva Papadogiannaki and Sotiris Ioannidis, and Eva is presenting them.
Hello everyone, my name is Eva Papadogiannaki. I'm affiliated with Fourth ICS, and right now I'm going to present you a teaser of our poster outside. Now, let me first describe the motivation behind this work. As we all know, the adoption of network encryption is constantly growing. This means that traditional network inspection tools that focus on inspecting the packet contents are not that sufficient anymore, so they have to evolve somehow. Since in an encrypted network packet, we only have visibility over the packet headers. In addition, network traffic speeds are constantly increasing, so we need somehow to find ways to accelerate the packet processing technique. Now, in the state of the art, we find a gap. So first of all, there are works that focus on, are able to traffic, to process the encrypted network traffic by doing traffic decryption before the inspection. In addition, there are other works that focus on investigating the feasibility of classifying encrypted network traffic using machine learning techniques. However, these works, in the first case, are the processing is really expensive, and in addition, these techniques would cause privacy violation eventually. In the second case, the machine learning techniques do not offer a real implementation in order to be tested against real network traffic. So, in order to fill this gap, we propose our solution where first we build signatures that are generated using network packet metadata sequences, such as the packet sizes and the packet direction. Then we develop a network inspection engine that searches for these signatures against the live traffic. And in addition, we accelerate this packet processing procedure using commodity high-end GPUs. Now, regarding methodology and evaluation, I chose not to include any details in order to force you to come by our poster, and then we can discuss everything there if you're interested, of course. So thank you very much.
And the next work is by Antti Hakarki and Ioanna Skanzalveliou. So you are Antti. Ioanna is presenting 50%.
So this presentation summarizes the results of our physical MSc thesis. It's about it's about internal attacks and how we can mitigate in enterprises. Can insiders stop threatening organizations and their information systems? First of all, let's take a look at internal attackers or insiders. They know the system, they know the procedures, they know passwords, they know how the system works. So maybe they are authorized employees or they are external cooperators, so they know all this stuff. So they might misuse authorized privileges. That's why it's a significant threat for our organizations. So our study shows that internal attackers can be reduced if we remove from employees both the ability and the desire to harm the system. So we have to convey the culture to want to protect for employees, to want to protect the system itself, and also the knowledge of how to do it. We have to educate them how to protect themselves from insiders, not only not to be an insider, and the organization can remove capabilities, attack capabilities, and reduce threats by properly securing the system. So we have outlined some measures and counter measures to prevent insiders. Although it's quite complex because we need a multi-level strategy which includes security policies, procedures, technical controls, etc. We have lists of security practices as what is a security practice? Let's see, a security practice which use log correlation engine, etc. According to this practice, we have to we can apply a system to mitigate insiders. I can show you this practice on the poster. And a security policy against insiders, which covers 6 different sections, and which also is included in a model. We introduce a model, we propose a model to mitigate insiders. I can present better on the poster, in front of the poster, how all these entities are in turn. Yes, they come together. Okay, thank you very much.
Okay, and the next work is by Vaya Bustraka, Despina Hatzaku, Antigoni Maria Pitoura, Antonia Mogolu, Irene Papagenopoulou, Theoduli Teziru, and Athena Bakali, and Vaya is presenting, and Vaya is presenting.
Hello everyone, I'm Vaya Bustraka from the Department of Informatics at University of Thessaloniki, and on behalf of my colleagues and my supervisor, Professor Athena Bakali, I'm going to present briefly an indicative part of our research work under the GEC project, which concerns cyberbullying, hate speech, and online social breaches detection. As it is known, online social networks constitutes a breeding ground for the spread of several risks and threats, privacy and security, affecting quality of life, regarding information security, and increasing civic participation in data production and sharing. With the purpose of protecting minors from malicious actors in online social networks, we design and implement the GEC platform. As we can see, the GEC platform consists of 3 add-ons, and we have worked on the deployment of a malicious detection add-on. This add-on is based on the following methodologies. The first one is a framework which social networks and has exploit machine learning classification algorithms. Another methodology is unified deep learning classifier for hate speech detection, which was tested in multiple Twitter datasets and offers a high accuracy. Another methodology aims at online social breach detection with graph methods. And this graph consists of 3 components, which shows social breaches. And finally, the last methodology have used perverted just-eyes dataset to identify predator behavior in a conversation. The findings are shown in the table. Thank you for your time.
Okay, thank you, Vanya. And the next work is by Karioris, Giorgos Pitoura, and Dimitris Societies, and Karioris present.
Hello everyone, I am Karioris from my thesis work, and I'm going to talk about the provenance and more specifically about a new query language, Prof. Nowadays, a large volume of data are published on the web every minute. These data are from several different fields and are now available online for usually for free access and use. As this data comes from several different and uncontrolled sources, we should take for granted the heterogeneity in their format and in their quality. Therefore, there is a great need for evaluating the quality, the trustworthiness, the reliability, and the accountability of such data. In this setting, recording the provenance of data, which means that we record their history and the sources that contributed to generate this data, is of crucial importance. Until now, a lot of provenance models have been developed to support the different types of provenance information. Although these courts have addressed the problem of determining how provenance should be recorded and represented, the issue of querying data provenance has not yet been adequately considered. In our work, we define a new high-level structured query language called Prof, which allows the user to express provenance queries. In particular, Prof is able to answer queries such as identify the different ways to derive a specific data record, identify all data records whose provenance includes a specific data source, and identify all sources that originate from a data item referring to Donald Trump. In the slide, you can see also the Prof syntax for the aforementioned natural language queries. Thank you very much, and I'm waiting for you in my poster.
Thank you, Adira. And the next talk, work is by Dimitra Zoufakistou, Giorgos Pitoura, Theodore Bartos, and Dimitris Societies, and Dimitra is presenting.
Hello, my name is Dimitra Zoufakistou, and I will talk to you about my research during my PhD studies. First of all, we were motivated by the challenge of formalizing a methodology to extract meaningful information from online dialogues. And after we studied thoroughly the informational requirements of this challenge, we transferred those requirements in format performance, syntax, and terminology of a query language, which we have called ArcQL. ArcQL is a query language that targets argumentative data. Here we present an example of our target data. Our data model comes, the theory of our data model comes from the most common principles of the area of computational argumentation, which is a field that studies the human reasoning while arguing. And these principles have defined our most basic concepts in our data model. So, our knowledge base of our data model consists of a set of arguments and a set of relations among particular propositions which define a set of interactions between arguments. So ArcQL targets data that consists of structured arguments and their existing interrelations. So representative examples of our queries is this. Our language is able to answer queries like find arguments which attack the attackings of those have a conclusion, this one, which is expressed like this, or find arguments which have commonalities in their internal structure, for example, the verb set. And this is how we express this in ArcQL. We have formally defined the language, the semantics, and we have suggested a methodology for the execution, and for more details you can ask me in the post.